Semiconductor theory explains how a p-n junction behaves conceptually, but engineering a circuit requires moving beyond concepts into exact numerical parameters. We are building a step-by-step template to calculate three critical values: the built-in barrier potential, the forward bias current, and the reverse bias current. For this problem, we'll use a standard silicon diode at 300 Kelvin. Our variables include a donor concentration of 10 to the 17th, an acceptor concentration of 10 to the 16th, an intrinsic carrier concentration of 1.5 times 10 to the 10th, and a reverse saturation current of 10 to the negative 12th amps. Calculating these values allows us to compare the diode's internal limits against our design voltages, determining exactly when the component will conduct and when it will block. The first step in finding the barrier potential is determining the baseline thermal voltage, or VT. At room temperature, Boltzmann's constant times the temperature divided by the electron charge rounds to 0.026 volts. We will use this constant as our thermal voltage throughout the calculation. The formula for barrier potential, VB, is the thermal voltage multiplied by the natural log of the acceptor and donor concentrations divided by the square of the intrinsic carrier concentration. When we plug our specific problem numbers into the equation, the relationship between the doping concentrations and the intrinsic carrier levels becomes clear. To square the intrinsic carrier concentration in the denominator, use parentheses around the entire scientific notation value. 1.5 times 10 to the 10th squared results in 2.25 times 10 to the 20th. After dividing the numerator by that result, apply the natural log, the ln button, rather than the standard log. The natural log of this division is 29.12. Multiplying that 29.12 by our thermal voltage of 0.026 gives us a final barrier potential of 0.757 volts. Run these numbers on your own device to ensure your inputs match this result. This 0.757 volts is the specific energy wall established by the ions in the depletion region. Any majority carrier attempting to cross the junction must overcome this potential. Applying a forward bias reduces this barrier. If the external voltage is sufficient, charge carriers can breach the junction and flow through the circuit. To find the resulting current, we use the diode current formula. We'll calculate the flow produced by an applied forward voltage of 0.6 volts, assuming an ideal diode factor of 1. We place our 0.6 forward voltage over the 0.026 thermal voltage in the exponent, with our reverse saturation current as the leading multiplier. The exponent 0.6 divided by 0.026 is 23.07. Euler's number raised to the power of 23.07 is such a large value that subtracting the 1 inside the parentheses no longer has a measurable impact on the final result. Multiplying that exponent by our reverse saturation current of 10 to the negative 12th gives us 0.01 amps, or 10 milliamps. This 10 milliamp current confirms that the 0.6 volt external pressure was high enough to overcome the internal barrier and allow majority carriers to dominate the flow. To observe the diode's blocking behavior, we reverse the polarity by applying a negative voltage of negative 0.2 volts. We use the same diode current equation, but we substitute the positive VD with our negative 0.2 volt value. Dividing negative 0.2 by our thermal voltage gives us an exponent of negative 7.69. Euler's number raised to a negative power results in a value so small it is functionally zero. Subtracting 1 from this near zero value leaves us with negative 1 inside the parentheses. Multiplying negative 1 by our reverse saturation current yields a total current of negative 1 picoamp. This tiny result shows that the widened depletion region has successfully stopped the majority carriers, leaving only a negligible trickle of minority carriers. Our completed template shows 3 distinct states: a 0.757 volt internal barrier, a 10 milliamp forward flow, and a negative 1 picoamp reverse leakage. Comparing these shows the scale of the diode's control: 10 full milliamps in one direction versus essentially 0 in the other. Using these steps for any p-n junction problem provides the precise data needed to verify circuit operation. Now that we have these specific values, we can move to the next video to plot them onto a standard VI characteristic curve.